Assalamualaikum and hi guys, my name is Norhaslinda Binti Ruslan. I am from class AS2025A1. My friends and I, we will present about CHM 676, which is Organometallic Chemistry. We will going to present based on the chapter 6, which is uses of some organometallic compound. So for the first slide is the catalytic property of organometallic compound. So this chapter is state that the ability of organometallic compound to undergo the combination of oxidative addition and reductive elimination reactions that enables them to act as a catalyst. So what is the oxidative addition and the reductive elimination? For the oxidative addition is a process that increases both the oxidation state and the coordination number of the metal center. So while the reduction elimination is a process that oxidation state of metal center will be decreased while forming a new covalent bond between two ligands. So there are many organometallic catalysts that employ in the industry, for example, and the most of them work via the oxidative addition or reductive elimination reactions that is typically occurs in cycles. So for this chapter, we will going to discuss about four catalysts, for example of catalysts. So let's get started. So for example number 1, I will going to discuss about bicyclopentadienyl tantalum trihydride as a catalyst of the deuteration reaction of benzene. So in the figures, you can see that the roughly steps from the benzene by using this catalyst to convert into the deuterated benzene. This cyclopentadienyl tantalum trihydride is act as catalyst to produce deuterated benzene. It replaces hydrogen with deuterium D, which is heavy hydrogen isotope. The deuterated benzene that produced usually used as a solvent that have been used in NMR spectroscopy. Okay, so for the next slide, I will explain one by one about the 5 steps that consist to convert from benzene to the deuterated benzene. So for the first step is the stable catalyst, which is consists of 18 electrons, will lose of 2 atoms of hydrogen by using the heating process. It also called as reductive elimination. This process converted stable catalyst to 16 electron of Sp2TeH. So for the second steps, 16 electron of Sp2TeH will react with a benzene molecule. So it's called as oxidative addition. This process to produce 18 electrons of Sp2TeH2pH, which is where a phenyl group is bonded at the alpha of the metal. So for the third step is the Sp2TeH2pH will undergo a second losses of 2 atoms of hydrogen, which is a reductive elimination. This process is to give another 16 electron species of Sp2TaPH. For the first step is the 16 electron of Sp2TaPH will be added by 2 atoms of deuterium, so it called as oxidative addition. This process is to form a 18 electron species, which is called as Sp2TaD2pH. So for the last steps, the stable Sp2TaD2pH will be eliminated to convert to the C6H5D, and another product is Sp2TaD. So the process will be repeated from the steps number 2 to step number 5 to form a deuterated benzene. So here's is the summary of the reaction, which is consists of 5 steps. So that's all from me. So next slide will be continued by my friends. Thank you guys.
Assalamualaikum and hi, I am Syazliana and here I want to present about Monsanto acetic acid process and its mechanism. Let's check it out. Here is the mechanism of Monsanto acetic acid process. Firstly, methyl iodide is being generated by the reaction between methanol and hydrogen iodide with the byproduct of water. Then, this methyl iodide will add to the rhodium complex by oxidative addition resulted to rhodium methyl complex. This rhodium methyl complex of the methyl is shifted to the neighboring carbonyl group. Becomes here. And the rhodium complex then become this acyl form with the addition of carbonyl. The acyl species undergoes reductive elimination to produce original rhodium dicarbonyl diiodide complex and acetyl iodide. Acetyl iodide undergoes hydrolysis to form acetic acid and hydrogen iodide.
Assalamualaikum, my name is Shamim Shahira Binti Aziz. I am from class AS 2025A1. Okay, I will continue with next slide, which is Wilkinson catalyst. What is Wilkinson catalyst? Wilkinson catalyst is a homogeneous hydrogenation. It was named after Sir Geoffrey Wilkinson, which Wilkinson catalyst is from the name of chloridotrous triphenylphosphine radium, a coordination complex of radium with the formula RHCl-PPH33. So next slide is the characteristic of Wilkinson catalyst. As you can see in the slide, that is the structure of Wilkinson catalyst. So the appearance is red crystalline solid, and then it is not soluble in water. The coordination geometry is square planar 16 electron complex, and the molar mass is 925 and 925.22 gram per mole. And then that is the chemical formula, C5-4H4 5Cl-P3RH. So next slide is how are we going to prepare the Wilkinson catalyst. So Wilkinson catalyst can be prepared by reacting hydrate rhodium trichloride with the excess triphenylphosphine in boiling ethanol. So the ethanol is served as the reducing agent. And then the application of this Wilkinson catalyst is used in the selective hydrogenation of alkene. I will show the example of the hydrogenation of alkene in the next slide. So this is the example. In this slide, it shows the example of hydrogenation of ethene. From ethene, it convert to ethane. So it is very active catalyst for the rapid homogeneous hydrogenation unsaturated compounds. It working rapidly at 25 degrees Celsius and 1 atm pressure of hydrogen gas. So this is the mechanism of catalytic cycle of hydrogenation using Wilkinson catalyst. It involves 5 steps, which is step 1, dissociation of one ligand, and then step 2, oxidative addition. Step 3, alkene coordination. Step 4, migratory insertion. And then step 5, reductive elimination. So I will explain one by one according to the step. So the first step is the association of one ligand. Wilkinson catalyst is a pre-catalyst that is converted to an active form by losing one ligand, which is triphenylphosphine, to give a 14 electron complex before entering catalytic cycle. So before entering catalytic cycle, the pre-catalyst must be in 14 electron complex. Then solvent molecule S will fill the vacant site. The oxidation state of RH in the middle of the catalyst structure is +1. Step 2 is the oxidative addition of hydrogen. Initially, the catalyst activate the molecule dihydrogen by oxidative addition to give a 16 valence electron dihydro complex. So from 14 electron complex, it converts to 16 electron complex by adding dihydrogen. And also the oxidation state of RH is increased to +3 after receive the hydrogen. Next step is step 3, coordination of alkene. So in this step, propene will added to give 18 electron complex. So in the first step, it is 14 electron complex. In the second step, 16 electron complex, and the third step, 18 electron complex. So next is step 4, migratory insertion. One hydrogen migrate and insert between carbon and hydrogen of alkene. This step is the rate determining step, RDS. And lastly, the last step, reductive elimination. Alkene is released rapidly by an irreversible reductive elimination step that completes the catalytic cycle. And then the oxidation state of RH is decreased to +1 and the catalyst is regenerated. So that's all for the mechanism of catalytic cycle, which involve 5 steps.
Hello guys, my name is Amira Faqihah. Today I would like to present about CHM 676 under chapter 6, which is uses of some organometallic compound under example 4, Wake oxidation of alkene to aldehyde. The general characteristics. First, process of producing acetaldehyde from ethylene using PDCl2, CuCl2 co-catalyst system. Internal alkene are usually unreactive, thus terminal alkene can be oxidized. Thirdly, the various terminal alkene can be used to oxidize the corresponding methylene ketone. The general Wake oxidation process, the first example show that alkene, which is ethylene, will react with PDCl2 as a catalyst, and CuCl2 with also act as catalyst with the presence of oxygen and water will produce aldehyde, which is ethanol. The second example show alkene, which is propene, will react also with PDCl2 as a catalyst and CuCl2 with the presence of oxygen, DMSO or water will produce a ketone, which is acetone. The diagram show the reaction mechanism, which show the cooperative catalyst cycle involve the oxidation of PD2, the oxidation of PDO by Cu2, and the oxidation of Cu1. Now, let me elaborate the step-by-step mechanism of the Wake oxidation process. In step 1, the complex formation will occur. The PDCl2 will convert to PDCl4. So basically, we will have lots of Cl- in the solution and will be able to coordinate additionally to the palladium. The solvent used is water. PdCl4 is a water soluble, so it can easily participate in the aqueous solution we have. In step 2, alkyl coordination happen. Coordination means sharing electron with that metal. The PdCl4 will react with the terminal alkene. In Wecker process, we must use terminal alkyl. The pi electron will be coordinate with the metal and form new coordination. In step 3, ligand exchange happen. Ligand is either the atom or compound that is coordinated or attached to the metal in the compound that we're looking at. In this step, we will exchange the chloride ligand with the water ligand. The more water you have, the more often this exchange will occur. Next, we will proceed to step 4, which is nucleophilic attack. The water molecule from within the molecule or separatively is going to come and interact with the compound we have, and we will deprotonate this process as well. The double bond will break and OH will attack to the bond. Move on to step 5, which is rate determining step. One of the chlorine is being removed, thus the palladium is being reduced. The palladium Pd2 plus will reduce to Pd plus. Step 6 involves the beta hydride elimination. The beta is the position relative to where the metal is. The metal here is palladium. The carbon adjacent to metal is alpha, while beta is the carbon adjacent to alpha. On the beta carbon, we are going to see one hydrogen, which is the beta hydride. Hydrogen is called the hydride when it has a negative charge because it will take both of the electron. The hydride will be eliminated and double bond will form. Step 7 involves 1,2 insertion. Insertion means this bond that already exists and some other compound or chemical entity is going to come in and place itself between two atoms of the bond. The palladium will be attached between the pi bond because the pi bond electron that will coordinate with palladium. Lastly, the final product will have a compound inserted itself between the bond that used to exist between the palladium attached to metal. In step 8, we will once again see a beta hydride elimination. The hydride on the beta position will move over the palladium and other bond will move up and make a double bond. The final product, hydrogen, will attach again to palladium and palladium coordinating to double bond between the carbon and oxygen. Next is step 9, which is reductive elimination. In this step, we will eliminate all the ligands of the palladium, and in this process, we are going to reduce it down an oxidation state of 0. The current reactant oxidation is state of +1 and all the ligand is eliminated. After reaction, palladium will have 0 state of oxidation. Until step 9, the product that we want, ketone, is obtained. Lastly is step 10. Step 10 is catalyst regeneration. Palladium has the oxidation state of 0 from step 9. Palladium will react with copper 2 chloride to produce PdCl2 and copper 1 chloride. Then, copper 1 chloride will react with oxygen and hydrochloric acid to produce water and regenerate the catalyst. That's all happen in the Wakey oxidation process.